All right. Welcome to Build Your Own SQLite challenge on CodeCrafters. In this challenge, we are going to build, something that looks like SQLite, not necessarily full-blown SQLite engine or library, whatever you want to call it. And there are a total of 8 steps. I'm hoping to record one video per step. We'll see how that goes. And as you can see, I've already attempted this challenge before. I went through these two steps, these two print number of tables and print table names, before realizing that I was going through a lot of interesting stuff. I was reading a lot of documentation. There were new things popping up left and right. So I thought I should record all of that and put it somewhere so that other people can watch it and maybe learn something. So yeah, I guess I'll put it on YouTube. Also, my last attempt here was in Python. Go is also available now. I don't think I'll choose Go. Mostly because right now I have an injury in my left hand and I don't type a lot of code, especially, repetitive code where you're constantly handling errors and all that. Otherwise, I quite prefer Go. Right now, I'll just do it in Python and see what happens. And there is also going to be a lot of reading, bumbling, not understanding things, I guess. All of that will be a part of the series. I am going to upload all of these videos unedited. Now, of course, if something goes horribly wrong or there is a lot of background noise, my neighbor decides to dig a hole or whatever, then I'll have to edit it. But otherwise, I'm not going to remove content. I'm not going to cut, say, my mistakes or areas, time spans where I'm mostly thinking and not writing code. That's kind of the idea. Not sure how good of an idea that is. This is also the first time I'm recording something, so I guess we'll figure it out all at once. Right. Okay. Let's do it then. So this is the Build Your Own SQLite challenge. The idea is simple. You need to build something that can query data from an SQLite database, maybe write to it. I don't think writing is a part of the challenge, but I believe Paul, by the way, is the person who is running CodeCrafters.io. He's building all of these challenges. He's maintaining everything. This is his website, his project. So I remember talking to him about this, and somewhere along the way mentioned that he was working on inserts, or maybe he was not going to work on inserts, something like that. Not sure. I forgot. So far, it looks like we only need to deal with reads. Okay, pretty standard CodeCrafters challenge. Select the language. It is going to initialize the Git repository for me. Copy the repository and okay. Let's go to our workspace and CodeCrafters. Clone this repository, move this to SQLite, and let's check it out. So pretty standard Python application, I guess. Actually, let me open this in my editor. Hang on. Okay, there it is. There is a readme.md. Let's go through all of these files one by one. Let's see. So the structure looks pretty minimal. There is codecrafters.yaml file. There is a sh file. What is it doing? Downloading a bunch of stuff. Downloading some databases for testing. Okay, and this one's just trying to execute your application, app.main, with all of these arguments. All right. Then we have sample.db. There's a database. There is a readme.md file. This is starting point for Python solutions. Okay, solutions. Okay. In this challenge, you'll build a bare-bones SQLite implementation that supports basic SQL queries like select. Along the way, you'll learn about SQLite's file format. Looks like the same description that is available in this step that was available, I guess. Yeah, it is gone. Passing the first stage. CodeCrafter runs tests when you do git push, make an empty commit and push a solution to see the first stage fail. You should see failure message. Okay. Go to app main.py and uncomment.db info command implementation and then push, and that should pass the first stage. All right. We'll get to that. Running your program locally. This is going to come in handy. Okay, so this your SQLite 3.sh file is going to execute that. All right. Let's close this. Cool. Sample databases to make testing queries locally. We have added a sample database in the root of this repository, sample.db. This contains two tables, apples and oranges. You can use this to test your implementation for the first 6 stages. You can explore this database by running queries against it like this. Okay. Or I guess I can just double click on it and see. What? I need to type queries. Yeah, I'm not going to do that right now. Ooh. Okay, this is bad. Okay. There are 2 other databases that you can use, superheroes. I think these are the 2 databases that are being downloaded in this file. These aren't included in your repository. Okay, because of the size. All right, that's fine. That's okay. Let's take a look at the app directory and other files generally. I think pip and pip file. Pretty standard pip file, no dependencies, nothing. Then there is CodeCrafters.yaml file, debug is false, language pack is Python 3.8, git ignore, nothing else. All right, let's take a look at main.py. Invalid Python interpreter. Let's configure our Python. Let's use 3.9. Let's use this one. All right. Creating virtual environment. Okay. All right. So what's going on here? What is this crying about? Relative import outside of a package. That's fine. It is 3.9. We are doing something. Import SQL parse available if you need it. Import SQL parse. Is that a Python package or are we doing something? We don't have any such module, so I guess that is a Python package. We'll learn about this too. We'll see. Oh, by the way, so I mentioned that I completed this 1 and 2, and I'm still. Let me rearrange this. 1 and 2, and I was able to do that without going through all of these details because it is really simple. Like you just uncomment a line. You'll see. You just have to uncomment a line and you can pass the first stage, and then you just copy and paste a bunch of stuff and you pass the second one. Third stage is where things begin to get a bit difficult, and that is also where I stopped. So so that I don't ruin everything. Right. So I actually don't know a lot about this code base. I don't understand a lot of these things. So I'm also learning along with, I guess, most of you guys, if you're watching. Right. Cool. So this is page header. Page header is doing something. It has a bunch of attributes. Then it has a function parse from, takes a database file, parses a page header as mentioned here. All right, let's take a look at this documentation. Yeah, that's a lot of documentation. I think there is a table somewhere, B-tree page header format. Okay, this. So this is the page header format. It says offset 0 size 1 byte flag at offset 0 indicating the B-tree page type, and that is what we are parsing on this line. Also, the data that is stored in SQLite file is in big endian binary notation. Big endian, if you don't know about that, means the most significant bit in your binary notation is at the tail end of the data. Hang on, let me find if they have an explanation for that. Database file. Oh, there. So the first 100 bytes of the database file comprise the database file header. The database file header is divided into fields as shown by the table below. All multi-byte fields in the database file header are stored with the most significant byte first. So that is big endian. Your most significant byte first means, well, it depends on how you're reading this. I actually don't want to get into this big endian and little endian because I also get confused at times when I begin talking about this. I think I'll put a link to Wikipedia article or something else that explains all of this in detail. And I think the concept of big endianness is not all that difficult to understand, but there are details as to which endianness is better in which situation. So for example, there are computations or streaming applications or some other applications where it is advisable to use one endianness versus the other because it is easier to perform operations on that format. And that's everything. The data itself does not change. I mean, you can read it from left to right and right to left, and it will still be the same thing. Just the endianness will change, right? So that we are reading this first byte that stores our page type. Hang on, I lost the database header, and then there's this. Right, so 1 byte flag at offset 0 indicates the B-tree page type. A value of 2 means the page is an interior index B-tree page. And don't worry about this, what is interior, what is leaf index, index or table or whatever. We'll go through all of this lingo once again. We'll have to read all of this anyways, so don't worry too much about that. It might not make sense immediately. It will soon when we get to that part. Right now, the only thing that you need to understand is that there are 4 possibilities. If the value is 2, then it means something. If the value is 5, then it means something else. If the value is 10, it means something else. And if the value is 13, it means something else altogether. Any other value for the B-tree page type is an error. So that is what we are doing here. We are reading the first byte at offset 0 and the Indianness is a big Indian, and we are using storing that as page type. Then we are doing the same thing for first free block start information. So it says offset 1, size 2, the 2-byte integer at offset 1 gives the start of the first free block on the page, or is 0 if there are no free blocks, right? And then we are parsing other information as well. Similarly, number of cells, start of content area, fragmented, free bytes. And again, don't worry about all of these things if they don't make any sense. So that's all right. We'll go through the documentation once again, and we'll understand exactly what all of these things mean. Like what is fragmented free bytes, what is start of content area, what is number of cells, or cells for that matter. So we'll learn about all of these. Right. So there is a class page header. It has a function. Okay. All right. Now, now there is this if block. So we execute the main.py. This is the code that will execute directly, and command is the second argument. The way we are supposed to execute this application is that we will say Python whatever the main.py, and we'll give it the path to the database file as first argument, and the second argument is going to be the command. And here we say, if the command is .dbinfo, then we do a bunch of stuff, and we print the number of tables, right? And what is this bunch of stuff anyways? We are trying to open database file path. Database file path is our first argument in read binary format. Then we skip the header section. So this header section is the database header, not the table header, not the page header. So there's a bunch of information that is stored in first 100 bytes. The first 100 bytes of the database file comprise the database file header. Right now, we don't care about that, so we'll just skip all of that. And then we'll parse the page header from 101 to whatever, I think that is 16 bytes. I'm not sure. Let's see, let's scroll to the bottom of the page. Ah, 8 bytes for leaf pages and 12 bytes for interior pages. All right, so not 16. Depends on the type of page, right? We are parsing page header, and then we are skipping database header and B-tree page header, right? So in this case, I think we're just assuming that this is a leaf page and there are no interior pages, right? Right, so we'll skip all of that, and then we are trying to load cell pointers. So database file.read 2 more bytes for range in page header dot number of cells, right? So we are doing something that, don't worry about it. We are doing something, we are loading cell pointers. Then for each cell pointer, we are doing something database file.seek number of bytes in payload. That is not used, but we'll have to use it down the line. We are trying to find other information. Then we are loading SQLite schema rows. So in the schema, we have some information, the type, name, table name, root page, and SQL. This is your standard information that is stored alongside each page. Hang on, let me show you where that is. Yeah, so that SQLite schema, type name, table name, root page, and SQL. And SQL simply means the column stores SQL text that describes the object. The SQL text is create table, create virtual table, or whatever create statement that, if evaluated against the database file when it is in the main database of a database connection, would recreate the object. So your exact same SQL that you use to create the object is stored in this column, right? Root page column stores the page number of the root B tree page for tables and index. So what that means is that whatever this root page number is, if we go to that page, we'll find the payload for this table there at that position, right? Your table name is the name of a table or view that the object is associated with. And then there is name. Name will hold the name of the object. Unique and primary key constraints on table cause SQLite to create internal index with the name of the form, this. So for example, if we are looking at an index, then the name is going to be something like this, versus if we are looking at a table, then the name is going to be a table. What is it? Sorry, not table. The name is going to be the name of the table. Then there is a type, and type is simple. Type will be one of the following text strings. Table index view trigger according to the type of the object defined. The table string is used for both ordinary and virtual tables, right? So a lot of information there. We don't have to remember all of this. We can always come back and read about this when we need it. Just know that all of this information is coming from SQLite schema. Then there is a print statement. Uncomment this code to pass the first stage. The code is simply number of tables is length of SQLite schema rows. So length of this is a number of tables. And if we give it something else, if we give it some other command, it is just going to say invalid command, right? So that is our main.py. Now there are two more files, and these two more files are mostly helpers, but let's just take a look at these files. There is one file that helps with, where is it? I really don't know about this. Let's just go to this. There is parse record and parse variant, right? Parse variant and parse record. So what's going on here? It says parses SQLite's record format as mentioned here. Let's see what is this. Okay, this is record format. The data for a table B tree leaf page at the key of an index B tree page was characterized above as an arbitrary sequence of bytes. The prior discussion mentioned one key, and again, it is referring to some prior discussion. We'll get to all of that. Actually, let me just get to this this record format. So what it says essentially is that you have a record, and the record has two meta attributes sort of about this. One is the type, and the other is value, right? And if you look at this table, it says the type code of the record format. If the serial type is 0, content size is 0, then the value is null, right? If the serial type is 1, content size is 1, then the value is an 8-bit 2's complement integer. That means it is a signed integer. Then all of these are again different bit 2's complement. Everything is big Endian again. If the serial type is 7 and the content size is 8, value is big Endian IEEE 754 2008 64-bit floating point number. Okay. Right. So these are the simpler ones. If serial is this and content size is this, then this means that, right? Simple enough. Now we get to these three slightly complicated ones. So serial type is 10 or 11 and content size is variable, reserved for internal use. So we'll just ignore that. If serial type is greater than equal to 12 and even, and content size is n minus 12 by 2, then the value is a blob that is n minus 12 by 2 bytes in length. Okay. If the serial type is greater than equal to 13 and odd, and content size is n minus 13 by 2, then the value is a string in the text encoding. Let me open that link. We'll get to that. And n minus 13 by 2 bytes in length, the null terminator is not stored. And we don't need to worry about this specifically. We can just, yeah, we don't need to worry about this in Python. Right, so let's take a look at this text encoding. What are these encoding? 4-byte big Indian integer at offset 56 determines the encoding used for text stored in the database. Value of 1 means UTF-8, 2 means UTF-16, LE, I never heard of this one. Value of 3 means UTF-16 BE, no other values are allowed. Okay. So just UTF-8 or the 16 LE, 16 BE. That's simple enough. All right. Right. So this parts record is, it takes a stream of some sort and column count. And it says parse variant stream, number of bytes in header. And then it says this many times, whatever the number of columns, that many times, we are going to read something from stream and figure out the type of that stored object, right? Of that column. And then we are going to return a list of parse column value. We are going to return a list of values. Hang on, I think I'm getting confused. Number of bytes in header, okay. Serial type, we are reading something we are loading serial type. So this is parse variant, and parse variant is simply it is trying to parse a variable integer. And for that, the spec is also pretty standard. So it says 64-bit 2's complement. There are some corner cases. Let me see. A variant is between 1 and 9 bytes in length. The variant consists of either 0 or more bytes which have the high order bit set followed by a single byte with the high order bit clear, or 9 bytes, right? So the variant consists of either 0 or more bytes which have the high order bit set followed by a single byte with the high order bit clear, okay, or 9 bytes. Okay, so if the number of bytes is less than 9, then this holds true. Otherwise, it will just have 9 bytes, and we can simply assume that there are 9 bytes. We'll just read all 9, and that's that, whichever is shorter. The lower 7 bits of each of the first 8 bytes and all 8 bits of the 9th byte are used to reconstruct the 64-bit 2's complement integer. Variants are big Indian. Bits taken from the earlier bytes of the variant are more significant than bits taken from the later bytes. Okay, right. So again, quite a lot to understand, but let's just go through this code. So what are we doing here? Read usable bytes. Again, since it says it is between 1 and 9 bytes, and it is either less than 9 or 9, whichever is shorter. If it is less than 9, then terms and conditions apply. Otherwise, just 9 bytes. So what are we doing here? We are trying to read usable bytes. So I will just range on it and we'll say read a byte in big Indian notation, usable bytes dot append. If the byte that we just read starts with 0, And where's that? Either 0 or more bytes which have the high order bit set followed by a single byte with the high order bit clear. Right, so that's what we are checking. If the high order bit is clear, then if it starts with 0, we are just checking that using this bit mask, then break. Then we have all the bytes we can use. That means the usable content ends here, otherwise keep reading. And once we have read all of these 9 bytes, then we'll just return anyways, right? This, by the way, is we have these two masks. The first one says, the first mask tells us if when we apply this mask. So those of you who don't understand binary operations and bit masks, is a simple idea. We have this mask, we are calling it is first bit 0, and this is the mask, right? So how do you use this? We use this by, so we have this another byte, and this is AND operation. We are trying to AND our byte with this. Now what is going to happen is, whatever is the content of our byte, let's say the content of our byte is, say, I'm just going to type a comment here. So this is our mask 1 0 0 0 0 0 0 0, right? And let's say our bit is 0 1 1 0 0 1 0 1, right? Something like this. Now we need to find if the first bit is 0. So what are we doing here is perform a bitwise AND operation, and let's see if, right. So since all of these bits are 0, when we AND these two bytes, 0 and 0 is 0, 0 and 0 is 0, 0 and 0, 0 and 1 is 0. So this one gets, the AND operation will take 1 and 0, and the AND of 1 and 0 is 0. True and false is, well, not true and false, but that is how the AND gate works. It is only true if both of the inputs are true, if A and B, right? If one of them are false, then the result is false. So same thing is going on here. We are looking at this byte and this bit and this bit, and one is true, the other is false. One is 1 and 0, the other is 0. So the answer is going to be, let's do this, 0. Then we look at this one, 0 and 0 is 0. Then we look at the third one, third from left, 1 and 0 is 0. This one is also 0. Actually, these 7 are going to be 0 because our mask says all of these are 0. So it doesn't matter if all of the content of these bits does not really matter, because our mask says all of these are 0. So when we AND all of this, it will automatically turn everything to 0. Now the only thing that can actually change this result is this last bit, and the last bit in our mask is 1. It is 1. Right. So if, let's say, if this bit was 1 in our original byte, then this value would be 1, right? If this bit was 0, then it would turn out to be 0. And this is how we can figure out if the first bit is 0 in any given byte. what we do is perform a bitwise AND operation and check if the answer is all zeros, right? That is what we are doing here. Perform a bitwise AND operation and check if the answer is 0. Let's get rid of this. Then we are doing something similar with this bit mask, last 7 bits mask. All of these are 1, so they are going to preserve the bits of the byte that we are checking against, and this one is 0, so whatever value we AND with this 0 will always turn out to be 0, right? Right, see this. We'll get to that in a minute. Okay, so read usable bytes. We have some usable bytes. And that was a detour. Right, so we have some usable bytes. Now, if usable bytes sorry, hang on. Oh, so now we are down to this part. Now we're trying to do this, right? The lower 7 bits of each of the first 8 bytes and all 8 bits of the 9th bytes are used to reconstruct the 64-bit 2's complement integer. So that is what we are trying to do here. Now, bit shifting operation is, well, I can again go on 5 minutes rant, but bit shifting, if you don't know about this, otherwise feel free to skip for like, I don't know, 2-3 minutes. Bit shifting works like this. If you have a byte, 2, 3, 4, 5, 6, 7, 8. If you have this and you left shift to this, left shift once, you get this. So you're shifting that 1 to left, and then you do the same operation again, you get this. What's happening here is you're effectively multiplying this value by 2, right? So what you're doing is, if you look at this, binary 1 is 1, binary 10 is 2, and binary 100 is, if you start from this, if you start counting, is 1 is 1, 10 is 2, 11 is 3, and 100 is 4. So you're multiplying by 2, right? And if you keep going, you'll keep multiplying by 2. Like that. So that's what we are doing here. Right. Yeah, so nothing magical. It is all according to the spec, because the data is stored in a way that we need to reconstruct this value. So that is what we are doing here. And that is how you parse a variant. Okay, what were we actually doing? Right, we are looking at this parse record. So you find number of bytes in the header is, I think, not used. Yes, not used. You're trying to parse a record according to the specification, and you read the type of the record, and then based on that type, you read the value of the record, and you return all of that in a list. That's what's going on here. Right, let's move on to the next file. I think you're taking a look at this one and this one. What do we have? We have this YAML file, bash file, pip file, readme. Okay, nothing else. Cool. So let's go ahead and pass our first stage and comment this. And Let's see. All tests ran successfully. Stage 1 test passed. Cool. Let's go back to CodeCrafters, listening for git push. Do I need to okay, it is reloading. Cool. And now we are at this second stage, print table names. And so this one is quite easy. Let me show you in this video, and then I will stop the video there and I'll start working on this one in a separate video. So what do you want to do here? We want to implement a new command, dot tables, that will print a list of all of these names of all of our tables in database, right? And here's the output it expects: table 1, table 2, table 3. Of course, not exactly this, but this is the structure of the output. The exact names of the tables can vary. You can test this with sample.db that is available in your starter repository, SQLite 3 sample.db .tables. It should print apples and oranges. Notice how the table names are formatted with more than one space between each other. That's because SQLite 3 formats its output so that every value has a fixed width, and we don't need to do that. Your program does not need to mimic this behavior. Using just one space I separator should work. Both apples space oranges and apples bunch of spaces oranges will pass our tests. All right, so let's see how that is done. We need to implement dot tables. This is for db info, and we'll just add let's be consistent with the quotes, dot tables, right? Now this one actually you can copy all of this and just use this exact code. Don't worry about code duplication right now at this point. We'll refactor all of this quite aggressively actually, because we need to reuse a bunch of stuff that's going on here. What is this? Duplicate, yeah, we know. Your code goes here, remove this, uncomment this, right. So we need to print the names of the table, and we'll just say join each dot, actually use subscript pbl underscore name for each in SQLite schema rows, and that should be it, right? Let's execute this. Your SQLite.sh will give it a what is the name of our test database? Sample.db. Oops. What? Code for HashMD5 was not found. Oh, that's because we are using 2.7. Let's activate our virtual environment. All right. What's going on here? Exec pipen. Okay. We'll install pipen in our virtual environment. What about now? Okay, looks like it blew up. Pipen found itself running within a virtual environment. Okay, that we know. That's okay. So there's a problem in our code. Print or join each table name for each in SQLite sequence item 0 expected string instance bytes found. That's all right. dot, is it encode or decode? So we have bytes. Do we encode bytes to string or do we decode string from bytes? Let's try decode, and we'll say UTF-8. Okay, we have apple, SQLite sequence, and oranges. I think it is fine that we're printing this SQLite underscore sequence table. We also have apples and oranges. Cool. So that is this second stage, print table names. Let's push that. All right, let's see. Cool. Stage 2, running tests, print table names, your SQLite.sh, test.tb, tables, butterscotch, chocolate, coffee, grapes, pistachio. Your program, test passed. All tests ran successfully. Congrats. Well, thank you. Okay, print table names completed. And now we are at the third stage, and this one is actually a slight bit complicated. Let me read this description and then we'll stop the video there. Now that you've gotten your feet wet with SQLite database file format, it is time to move on to actual SQL. In this stage, your program will need to read the count of rows from a table. Here is how the tester will execute your program. A bunch of things, and here's the output it expects. All right. Again, not exactly this, but something like that. Exact value will change, of course. You'll need to read the tables row from SQLite schema table and follow the root page value to visit the page corresponding to the table. Now, all of this might sound like a bunch of, I know what, but we have already been working with all of this. If you go back and look at this code, we are already parsing SQLite schema table. Oh, sorry, didn't mean to click on that. And we already have root page value that is here. We actually have all of these other tables as well, because we just printed the names of these tables. So this SQLite schema rows is already parsing all of this information, right? So we can just start using it right away. For now, you can assume that the contents of the tables are small enough to fit inside the root page. We'll deal with this with tables that span multiple pages in stage 7. Stage 7 is retrieving data using a full table scan. Remember, you don't need to implement a full-blown SQL parser just yet. All right. Again, I think I will try to be generous with the amount of code that I write, but I'm trying not to write a lot of code. I'm trying to solve this problem with as few lines of code as possible for me. That is something that is a personal challenge. It does not actually mean anything to anyone. I'm just trying to do it that way. I'm trying to see what is the minimum number of lines that you can use to pass all of these stages, and in that I might make some decisions that might look like cutting corners, and of course there will be, but again, if you don't have to do something, don't do it. If you're going through this challenge, only do something if you really need to do it. Otherwise, first of all, it is really easy to go down rabbit hole and get lost with this database file format, query parser, query optimizer, data fetching engine, understanding these pages and indices, and a lot of stuff that's going on here. Then you'll also learn about this whole thing, this storage format. It also has provisions for plugins, and that is again another interesting thing that is worth looking at. You can also read about write-ahead log and how the transactions are handled, how the rollback journal works. All of this is interesting stuff, but you don't have to get into all of this. Follow the advice. You don't need to implement a full-blown SQL parser just yet. It is fun to write parsers. We just don't have to do that right now. It also says just yet, so there is something. We'll get to that in next stages. For now, you can just split the input by spaces and pick the last item to get the table name. All right, so we'll do that in our next video.